Welcome back to our series on random walks. This is the animation that we got last time with Kramer and Josh, each taking random steps up or down in the Y direction. And basically you get a different animation every time because you're going to get a different set of random numbers every time. Here we're graphing their motion. You can see they just recently crossed each other. And basically they're moving independently, right? So you've got two independent random walks going on. Josh was hovering around 0 a little bit before. Kramer's was hovering around 0 a little bit here. And basically this is the type of motion that you would expect. And again, this is useful for things like the stock market or diffusion. Anything with a random element to it, you can model as a random walk. And I gave you a preview last time of what we're going to be doing today. Today what we're going to do is we're going to expand this. So instead of just having two random walkers that we watch in detail, we're going to have a lot of random walkers. So this is an expanded version of the code from last time. We still have our function up or down. So this is the heart of the random walk. Again, it's a coin toss. 50% chance of going up, 50% chance of going down. And we're going to set up 100 random walkers, and we're going to keep track of that with a list here. Lists are pretty useful in Python because you can store anything you want in a list. So here we're going to store the value of each of those walkers, which step they're at. And here we're going to store all of the graphs. So we've got two very different things stored in lists. And basically what we're going to do is we're going to start each walker off with a value of 0. So everybody is starting at y equals 0. Nobody gets a head start. Nobody starts behind. Everybody starts at y equals 0. That's one of the assumptions and the results that we're going to look at in a little bit. And then we're going to create a graph for each random walker. So each random walker gets a graph on our display window. We're not going to bother animating 100 spheres. We can do that if you want, but I don't think that's going to be terribly insightful. And then we're also going to keep track of the average position and the average distance. Let's talk about what that is in just a minute. So just keep an eye on those for a little bit. Now, I've simplified this from last time. Last time we had a time step and a y step that were both, I think, 0.1. In order to look at the statistics that we want to compare to today, we need to have steps of 1 in both the time and the distance axes. So we're just going to have that be 1 for now. So we're going to start at n equals 0. So n is going to be which step we're on. So this is the current step. And this is going to be, the random walk step. So this is going to be the step number. So everybody's going to have the same step number. This is time marching forward. This is where x is going to be where everybody is, or the walker's value is going to be where everybody is. And just to keep things simple, we're going to loop this not forever, but just for 100 steps. We're going to increment in here so everybody has the same n value. And then basically what we do is we look over over each of the walkers. So this is going from 0 to 99. So we're getting our 100 walkers. And we're adjusting each walker's value. We're adjusting each of their locations by either positive dx or negative dx. So we're just modifying walkers of I by dx times up or down. Worry about the average stuff in a minute. Then we're updating the graph here. And so what we're going to get is 100 graphs of a random walk. So you see they all started out at 0, so they initially all move to 1 or negative 1. And then they move from there, they can move up or down there. So this kind of gives you an idea of kind of the cone of possibilities that they've got. So you can think of it like if somebody were to get all positive 1s, not terribly likely, but if a random walker were to get all positive 1s, they would follow this line all the way along here. If somebody were to get all negative 1s, they would follow this line all the way down here. And of course, most random walkers don't do that. Most random walkers get a pretty even mix of positive 1s and negative 1s. So you see this kind of lattice in the middle where random walkers are moving up and down, they're passing each other, etc. But, like in a region here, it's pretty dense where kind of every spot is occupied at each one of these steps. Then you get a little space like this where nobody is stepping, and then you get these pretty empty spaces like this corner and this corner where there's nobody at any of these values. So if you kind of think of this as like people walking down a street, each one of these values along the vertical axis is a different building that they're visiting. So here, there's nobody visiting the buildings in this stretch of the street. And it kind of makes this cone. It's pretty cool. People tend to not go marching up in one direction for very long. They end up, turning around. So it's a pretty neat shape. I mean, if you wanted to generate some random coloring patterns for kids, this would be kind of a fun way to, design kind of a randomized coloring book. So that gives you an idea of the general shape, but we can be more specific than that. There's a couple things you expect to get from the statistics here. One of the things you expect to get is that if you take at every instant, so at every n, if you take the average of all of these random values, you should get approximately 0. Because you're basically averaging out a bunch of positive ones and negative ones that are equally likely. So when you add up an equal number of positive ones and negative ones, you get 0. And so that's what we're graphing here in the average position in the blue. So let's take a look at how we're calculating that. We started out with average position equal to 0. And basically for each walker here in this loop, we're adding that walker's value to the average position. And then at the end, we just take that value and divide by the number of walkers. Average is just the total divided by the number. And so that's what we're graphing here in the average position graph. Is the average position for each step in the while loop, so for each value of n. And you notice we get it hovers around a little bit, but we pretty much get 0, right? So depending if the population is shifted a little bit up, you get one that's a little bit higher. If the population shifted a little bit below, it's a little bit lower. But we're not getting, an average of -10 ever. We're staying pretty close to 0. The other thing you can look at is the average distance. So this is a different thing than position. Position cares about whether you're above 0 or below 0. Distance just cares about how far away you are from 0. So for example, right now this point is right at about negative, I guess that's a -11. And this point up here is at a positive 11. Those points have the same distance. They're both 11 units away from 0. It doesn't matter that one is below and one is above. The important thing is how far they have walked, meaning how many steps they would have to take if we called this experiment off and all the walkers had to return back to home base. So in order to keep track of that, we use the absolute value function. And basically, absolute value takes any number and chops off the negative sign. That's the simplistic way of thinking about absolute value. So here it's the same process as calculating average position. We're just adding the absolute value instead. Here we do the same thing. We divide by the number because the average is the total divided by the number. And here we're graphing that. And basically, if you do the math on this, we won't do this on screen. I'll include some links to some articles that do this. But basically, if you do the math on that, taking the average of adding up a bunch of positive ones and negative ones and just taking the absolute value of the result, you should get something that's equal to the square root of 2 over pi times n. So this is kind of a neat result. This is pi showing up in a problem that doesn't have anything to do with a circle, at least not on the surface. It doesn't have anything to do with a circle. So if you're doing a random walk in 1D, your sort of average distance from 0 should go like the square root of n multiplied by square root of 2 over pi. And that's what we're graphing here. So what I've done is I've made 2 graphs for this. One is a g-dots. So g-dots is a graph that just returns dots, so just returns points. That's the average distance, and those are going to be in red. Then we have a g-curve, something that's going to return a line, also in red, and that's what it should be. So this predicted distance graph is what it should be, 2 divided by pi times n, all square rooted. So basically, if these dots line up with this curve, then we are successful. So let's see, I mean, you already saw it happen, but let's check it out here. Notice we've got our line, we've got our red dots. They track each other pretty well. Again, they go a little bit above, a little bit below, but for the most part, it's following this square root curve. So this is actually a pretty neat process. What this means is you could conduct this experiment and then invert that equation and get pi. So you could calculate pi just by getting a bunch of people on a street, having them flip coins, go to different spots on the street based on the coins, and you could use their average distance to calculate pi. That's pretty cool. All right, so that'll be it for today. We're going to take a look at some more tests with this. We're also going to start expanding our random walk out into 2 dimensions, 3 dimensions, and even a video where we expand it into 4 dimensions. And I'll let you wonder how we're going to do that on a 2-dimensional screen. So thank you so much for watching. I will see you next time. Bye-bye.